So good morning, everyone. So can you guys see my full screen? If yes, please type yes in the chat window.
Yep.
But yeah, thank you. Yes, yes. Great. Yeah, thank you all. So good morning, everyone, and I wish you are going well. And this is our second week and lecture 4. So today will be our last lecture to introduce Matlab fundamentals. If you are already very familiar with Matlab, that's great. If you're new to Matlab, so you also don't have to feel any pressure, and it's very common that you cannot remember all the commands in just 2 weeks. So all you need to do is just practice, practice, and practice. And so before we start, I'd like to answer a few common questions. I saw some students sent me some questions, and they're very similar, so I will answer them now. So first of all, so our graders have office hours now, weekly, for Shravani, the current schedule is for her is Friday from 2 to 4 p.m. And for Kushel, his current plan is Monday from 4 to 5 p.m. and Wednesday from 11 to 12 p.m. So if you have any questions, you can also reach out to them. And I mean, if both of you are on campus, maybe you can schedule an in-person meeting. And if you prefer a Zoom meeting, you can also schedule the Zoom the meeting with them. And so is there any question for the office hours? Great. So for my office hours, it's just after the class. So is there a link to them? Good questions. I will let them to post the link in my courses announcement. So yeah, they may use their own link. And also for my office hours, it's just after the class by Zoom. If you don't, I mean, if you have other schedules, you can also send me an email, and we can schedule another time for us. And the second one is the quiz 2. The quiz 1 is due today, if I remember it correctly. And it's just some very you may notice it's just some very fundamental questions in the first week's lectures. And the quiz 2 will be posted by the end of this week, and it will be very similar, just some common questions we discussed in for Matlab. And I saw some emails asking me about the recorded videos, and as I mentioned, the recorded videos are already uploaded to the YouTube, so it's unlisted. So it's only for internal use, for the students in at RIT in this CS631. So you can watch the videos on the YouTube, and I will post the link to the announcement. So if you want to watch the previous videos, and you can just click the link, and I think you will be able to watch the videos. So if you have any access issue, just let me know. And so we have another question from Michael. So we should be ready to take quiz 2 after today's lecture. I think so. So yes, so for the quizzes, the objective for the quizzes is to help you review everything you learned in the past week. So you should be ready to take it. Yeah. So you can expect the quiz 2 to be posted, before the Sunday. Yeah. So any other questions? Great. Great. And also I noticed we have some new students who just enrolled in this class. So don't worry if you missed the first 3 lectures, and you can watch the videos on the YouTube. So, and also remember, this is only for internal use. Please don't share it with the others. Maybe your friend, maybe your student, maybe your classmates, but not others. Okay. All right. So let's start. And before that, let's review what we discussed on Tuesday's lecture. And remember that on Tuesday, we discussed the digital image and image coordinate system. So now I wish you can remember the difference between the digital image coordinate and the spatial coordinates. And also we briefly mentioned how to read, display, and write an image. We also discussed some image data types like double, like float, logic, and also like integer, as an integer 8. We also covered the interactive input and output, and we discussed the input function, the text scan, and the G input. You may not use them in your future homeworks, but it's good to know in Matlab we have some functions like this. And we also discussed the plotting functions in the 2D and 3D. We covered the mesh function and surf function. So if you already forgot what they mean, so you may want to review what you learned on Tuesday. And for today's lecture, here's the outlines for our today's lecture. And I will show you some example for the G input function. And also on Tuesday for the digital image types, we discussed the grayscale and the logical image. And today we will discuss the RGB, the 3-color images, and also the indexed images. And also it's called the pilot or color mapped images. And then we will cover the logical and the linear indexing for Matlab. And I will briefly mention some operators, the format, and also cell arrays, structures, and the tables. And that will be all we want to discuss for the Matlab. So first of all, I want to mention the G input function. And remember that for the G input function, the output is a 2-dimension array. So the first one is the columns, and the second one is the rows. And to input data, this function is to input the data by using a mouse, and we used the function G input. And this function displays mouse-controlled crosshairs superimposed on the current figure. For example, here's an example. And once you ran this function, you will be able to see the mouse-controlled crosshairs in your image. And each click will record the column and row coordinates of the center of the crosshairs. So after you type in the enter, it will terminate the input with C and R being a K/2 matrix. Let me start my pin. So the output of this function will be the column, the rows, the dimension will be K/2, and because it's just a two-dimension X and Y, or the row and the column. And K is the number of the points that you sampled. So also I want to mention that, so some students ask, what's behind the G input function and what's the code? So in Matlab, you can find that by using the help function, the doc function, you will be able to see how the G input works by the original code. But I want to mention that usually you don't have to understand the basic code behind this function, as long as you know how to use this function for your projects, your homeworks, then you are good. But even for the real research, it's enough to know how it works, and you don't have to understand how to build these functions. But if you are a programmer or coder, you are interested in how it works, feel free to find it, to invest more about it. Yeah. So in this example, we write a function that accepts an image name from the keyboard, display the image with the superimposed crosshairs. It allows the user to use the mouse to move the crosshair and to sample the coordinates at the center of the crosshairs. So that's what G input does. And second, remember on Tuesday, we mentioned that there are 4 image types in Matlab: the binary, grayscale, which we have already discussed on Tuesday. And today I would like to cover and also remember that grayscale image is a data matrix whose values represent monochrome intensities. We also call the shades of gray. When the elements of a grayscale image are, for example, of class S and integer 8 or S and integer 16, they have integer values in the range from 0 to 250. And for this one, it's 0 to 265, 534, if I remember it. Yeah. So also we mentioned that binary image has a very specific meaning in Matlab. A binary image is a logical array of zeros and ones. And so that for those things we discussed on Tuesday. And today we will cover the RGB and the indexed image. So first of all, let's talk about the RGB image. So that's something we will also discuss in our following lectures, the color, The color we perceive an object to be is the result of a very complex interactions between the light of an illuminating source. What happens to that light when it hits and is reflected from the object, and the human visual system, and the illuminating source or illuminant might be for example, might be the sun, or the cloudy sky, or even an LED light. So the object may reflect, absorb, or transmit some of the light. So when reflected light from the object arrives at our human eyes, it will stimulate the light sensitive retinal cells that then transmitted signals to the visual processing centers of our brain. So to at least some degree, these interactions can be modeled and analyzed to understand and predict the human response to color. So that's why we can have detect for the visible light is usually from like in this range. So as this figure shows, no color in the spectrum ends abruptly, rather. So each color blends smoothly into the next. This visible light spectrum is also called electromagnetic radiation in a specific range of wavelengths. For example, for the blue and violet hues, usually they are below the 480 nanometers. And for the green, usually the range is from 480 to 560 nanometers. And for the yellow is between like 560 to 590 nanometers. And orange from 590 to 630. And red are located about like 630 nanometers. And for the ultraviolet light, which is filtered out by some sunglasses to protect your eyes sometimes. So in this range, it's usually below 400 nanometers. And for the infrared light, which is detected by the night vision equipment, is in the range just above 700 nanometers. You may wonder why we care about the spectrum, the colors. Actually, it's because that in the real world, as I mentioned, the object will reflect the light, right? And for different objects at different wavelengths, it will give us different reflectance. And sometimes, for example, in the real world, for agriculture research. So if you see the bottom left is a sensor called MechaSense multispectral. It's called MechaSense. This is a multispectral camera, which has 5 different bands or 5 different wavelengths, which is green, which is red, green, blue, and near infrared, and red edge. So for those different wavelengths, the reflectance will be very different. If you see that, you can see this curve looks like this. For the crops, for example, when we want to detect if the crops have disease or if there's something wrong with the crops, we will measure the reflectance from the crops. And for example, for healthy crops, maybe they will have a higher reflectance for the near infrared band. And for the near infrared, we call it NIR, near infrared band, which is kind of in this region. And so for healthy crops, usually they have a higher reflectance. But if they have disease, their reflectance will be slower, will be much smaller. Maybe the reflectance will be something like this. So in this case, by measuring the reflectance, the near infrared reflectance, for example, once we got the data set, by using some classification models or some other machine learning algorithms, we can classify the difference between the healthy crops and non-healthy crops. So that's some very useful, very useful things you can get by using the color information. And yeah, so that's something about the art, the colors. And for the RGB, it's very straightforward. So in RGB color model, a color is described by three numbers, right? If an image has three channels, and it will be like the first one will be usually the first one will be red, the second is green, and the third is the blue. So that's how it works in Matlab. But in some cameras are very interesting, just like I mentioned in the previous slide. And for the megasense sensors, this is also common for some other sensors, you may notice that for the first channel is set up as blue, and the third channel is red. So don't feel surprised when you see some sensors in that color order. So it's very common, and you need to pay attention when you apply uh, the image information in Matlab or some other softwares. So like I mentioned, in the RGB color model, there are three components, and red, green, and blue. So these values indicate the intensities of red, green, and blue light sources respectively. So an RGB image usually is in M by N by 3 array of color pixels, where each color pixel is a triplet corresponding to the red, green, and blue component of an RGB image at a specific spatial location. So for example, here we used FR, FG, and FB to represent the three component images. And an RGB image is formed from these images by using the cat operator, which stands for the concatenate operator to stack the images. So the order in which the images are placed in the argument list, it matters. It does matter, okay? So in general, for the cat function, the concatenates the arrays along the dimension specified by the dimension argument. So the first argument is called dim, which means the dimension. So if dimension equals -1, the arrays will be arranged vertically, So if dimension equals -1, it will be arranged vertically. And equals 1, equals 1. So if the dimension equals 2, it will be arranged horizontally. And if it equals 3, it will just, as shown here, it will be arranged vertically. They will be stacked in the third dimension, as shown in this figure. So that's how the cat function works in MATLAB. So is there any questions so far? Oh, oops. Oh, I'm sorry. I think I lost. Let me share my screen. Oops, what happened? Give me 1 minute. I think we are lost. Okay, I think we are back. Let me share my screen again. So can you guys see my screen?
Yes, Professor.
Okay, good. Yeah, thanks for the feedback. Okay. So is there any question for the RGB image?
Professor, in the homework, I can see we have to divide the image with two channels, red and green. So there we have either we have, means does it means we have to use 2 dimensions, or it's like we have to still we need to use 3 dimensions while concatenating?
You mean your homework 0 or?
Yes, Professor.
I think for that one, you just follow, you can just follow the instructions, and for the red, I think they're all 3-dimension image for that, for homework 1. There's no, it's 3-dimension, yeah. And for this information, like in the future homework, for example, I may ask you to generate a grayscale image by using a single channel. So in that case, you can just choose one of those 3 channels, and it will display in grayscale if you just use one.
Okay. Thank you, Professor.
Yeah, no problem. And okay, we will continue. And the second one is the indexed image. So an indexed image, as I mentioned on Tuesday, it will usually has 2 components. So an integer data matrix and a color map matrix. So a color map, as I mentioned last time, is a C by 3 dimension. So this is a color map. So a color map is a C by 3 matrix of data type double with values in the range from 0 to 1. You can see that the range is from 0 to 1. So each row of the color map specifies the red, the green, and blue component of a single color. You know, the length, as I mentioned, the letter C, the length of the map is equal to the number of colors it defines. And the pixel values in the image matrix. So this is the image matrix. So the pixel values in the image matrix are direct indices into the color map. You know, therefore, the color of each pixel in the indexed image is determined by mapping the pixel value in the image matrix to the corresponding color in the color map. And the mapping depends on the data type of the image matrix. And if the image matrix is of data type single or double, the color map normally contains integer values in the range from 1 to p, where p is the length of the color map. So the value 1 points to the first row in the color map, and the value 2 points to the second row, and so on. So if the image matrix is of data type logic, unsigned integer 8 or unsigned integer 16, the color map normally contains integer values in the range from 0 to p minus 1. And the value 0 points to the first row in the color map, and the value 1 points to the second row, and so on. And in this figure, in this slide, the figure illustrates an index image and the image matrix and the color map respectively. And the image matrix is of data type double. So you can see that. So that means the value 7 points to the 7th row of the color map. You see that in the image matrix, for the pixel value when it equals to 7, this means it points to the 7th row in the color map. So that's exactly how the index image works. And to display an index image in Matlab, you can try using imShow function. And X is the image, and the map is the color map. So let's say how it works in Matlab. So here's an example to show you some flowers in Matlab. And so a color map is stored with an index image and is automatically loaded with image when the IMRead function is used to load the image. So sometimes, oh, is there any? I think I hear something.
Stop right here, burning my lunch.
Who's talking? I will mute you, okay? I'm gonna mute you. All right, let's continue. So sometimes it's necessary to approximate an index image by one with fewer colors. And for this, we use function IMApprox. Oops. And whose syntax is shown here. The IMApprox, and X is the image, the index, the image matrix, and the map, and N is an argument. In this function returns an array Y, and with color map, we call it new map, and which has at most N colors. We can define this argument. And the output Y is of class n integer 8 if n is less than or equal to 255, 56, 55. And if n is greater than 256, and the Y will usually be class double. So here I show you a example, and by read a default image in Matlab, and then we can display the original image in the figure 1. This is the original image. And then we convert this into an index image. So in Matlab, you can use RGB to index, this will convert your original image to a indexed image. So, and here you notice that my added an argument is non-deezer. So this is regarding to a technique called dithering in Matlab. So dithering is used routinely in the printing and publishing industry to give the visual impression of shade variations on a printed page that consists of dots. And in this case of grayscale images, dithering attempts to capture shades of gray by producing a binary image of black dots on a white background, or vice versa. And the size of the dots vary from small dots in light areas to increasingly larger dots for darker areas. So let's say these 3 different images. So on the left is the original image, and in the middle is the non-dithering image, and on the right is the dither image. So both images have only 8 colors, which is a significant reduction with millions possible colors of unsigned integer 8 image. And if you look at the middle image, it shows a very noticeable degree of false contouring, especially in the center of the large flowers. So if you look at this one, and for the background, and you see that this is kind of like a dark green area. And we can, so these are like the false contouring image. And if you look at the third one, the desert image in the third image, it shows better tonality and considerably less false contourings. A result of the randomness introduced by dithering. The image is a little blurred, but it certainly is really superior to the second image. And the effects of dithering usually are better illustrated with a grayscale image, but here we are using RGB, but it will be very similar. And so I will say that the dithering is kind of like a trade-off between accuracy of visual perception and the computational complexity. So that's something about the indexed image. So next, let's focus on some logical indexing. So another form of indexing that you will find quite useful is the logical indexing. A logically indexed expression has the form A, you can see that the A and D. So D can be a logical array, which is 1, 0, 0, 0, 0, 1, and 0, 0, 0. And A, we have an array which is A, which is 1, 2, 3, 4, 5, 6, and 7, 8, 9. And what and usually for D and A, they have to be the same size. And the expression, what the expression A and D does, it extracts all the elements of A corresponding to the one valued elements of D. So if you look at the result of this function, and because for the D, we have 1 in and here, and for the second row is the third column. So in that case, I'm not using this A. I'm actually using this A here. Okay. So if you look at the first row, the first element is 30, and the second row and the third column is 40. So by using A and D, so this will only extract the corresponding one valued location. So that's why it returns 30 and 40 for this array. And usually for the logical indexing method, the output of this method of logical indexing is always a column vector usually. So let's say another format is the linear indexing. A linearly indexed expression is one that uses a single subscript to index a matrix of a higher dimensional array. And to illustrate this concept, here I created a magic matrix, which is a 4 by 4 dimension array. And so for the linear indexing, what it means is that for the subscript, it starts in the column vector. So for example, for the 16th will be 1, 5 will be the second, 9 will be the third, and 4 will be the fourth. And for the second column, it will start from 5 and then 6, 7, and 8. So that means if you want to index to one of the elements, for example, M1, this will return the first element in the matrix, and M5 will return the 2. And when you type M15, it will return the first one and the fifth element of this array. So we want to remember this linear indexing thing, so that you won't be messed up in Matlab. So here is an interesting question for you. So everybody is wake up. So here's the question for you. So what if, so I have some row index and column index. What will MRC return in this case? So I'll give you 1 minute and try to think about this question. So if you have some thoughts or if you have some answers, you can type it in the chat window. So what will MRC return in this case? We have a a row index and column index. What is MRC in this case? So 3, 8, 15. So just 3 elements. Three, 8, 15. We have 20 seconds, 10 seconds. You still have 10 seconds. If you have some answers, you can type it in your chat window. Be my guest. That's okay. That's okay. Oops. Yeah, thank you. Yeah, thanks for your answers, everyone. And so this is a common mistake. And even for, even for me, I made the same mistake at the beginning. So, very straightforward thought. We may think about that, hey, this is a 3 index, right? And we should return 1, 3 to the first row and the third column is 3, right? The second row and fourth column is 8, and the fourth row and the third column is 15. So 3, 8, 15, perfect. So actually, that's not how Matlab works. And in Matlab, it's interesting that it will iterate through all the combinations, all the possibilities. So that means what MRC returns actually, it will iterate through the row and columns. So that means it will return 1, 3, and 1, 4, and 1, 3. So for the first row, it will return this. It will return a 3 by 3 matrix. And the second is 2, 3, 2, 4, and 2, 3, because that's the second one. And for the third row index is 4, so we will return. And the first column index is 3, so that will be 4, 3, and 4, 4, and 4, 3. So all I'm using is the index. So what it will return is actually this number. It's a 3 by 3 matrix. And the first one column is, in the matrix, is 1, 3. So for the first row, the third column is 3. That's why the first element is 3. And for the second, in the first row, the second column, the location is 1, 4. So that's why it will return 13. And for the third one is 1, 3 again. So that's why it will return 3 here. And similar for the second row. And let's do one more row here. So it will return the second row, the third column, which is 10. And the second row, the fourth column is 8. It's 8 here. And the second row, the third column is 10. So that's why it returns 10 again. So that's how MATLAB works by using linear indexing. So you want to be very careful when you use this, when you want to use linear indexing in MATLAB. So any questions for this demo? So it's very clear, right? Mm-hmm. Okay, we'll go to the next. Next.
One moment.
Oops. So the next one is a sparse function. So in MATLAB, when a matrix has a large number of zeros, it is advantageous to express it in sparse form to reduce the storage requirements. And function sparse converts a matrix to sparse form by squeezing out all 0 elements. So for example, if we have a matrix and it's 100, 034, and 020. We have many zeros here, and it seems that we don't want to display it. We don't want to display the zeros. So in this case, you can use the sparse function. And so you can try S equals sparse A, and S will contain only the row and column location of non-zero elements sorted by columns. And so for example, here we will return the first row, first column, the second row, second column, and the third row, the second column, and the second row, the third column. So remember it is sorted by columns. So that's why it goes in the first row, the second row, and then the third row. And if you want to recover the sparse matrix, you can just use full function in Matlab. By using full, it will display the original matrix. And also in Matlab, actually you can create a sparse function by yourself. For example, you can use the sparse function. You can custom the size of your original matrix, and you can decide the locations where you want to put the zeros or some values. You can decide that later. So try to use a help or doc function to find more about the sparse function here. All right, so let's go to the next one. So operators. So in Matlab, operators are grouped into three kinds of categories. So the first one is arithmetic operators that perform numeric computations. The second is the relational operators that compare operands quantitatively. And the third one is logical operators that perform the functions, for example, and, or, and not. So let's say arithmetic operators. So in Matlab has two different types of arithmetic operations. So the matrix arithmetic operations are defined by the rules of linear algebra and therefore limited to operations between one dimension and two-dimensional arrays. And element-wise arithmetic operations are performed between corresponding array elements and can be used with multi-dimensional arrays. And the period, the dot character, distinguishes element-wise from matrix operations. And arithmetic, relational, and logic operations between images usually are element-wise operations. And when performing an element-wise operation with two inputs, and A and B, the input must be either the same size or have compatible size. And I'll show you what compatible size means. But now you should know the difference between the element-wise and the next. So let's say an example to say what I mean when we do the element-wise. So here I have two matrix. The A is a 2x2 matrix, and B is just a scalar value. It's just one value. So when you say equals A plus B, and this is 2x2, and this is 1. And although they're different size, but in Matlab, this is called compatible size. So in this case, it will add 10 to all the elements in this array. So that's why we will return this new matrix here. So on the right side is another example. For example, A is a 4x2 matrix, and B is a 4x1 matrix. And although in this time it's also still they are not the same size, but because they are compatible, so that's why we can still calculate the sum of A and A plus B. In this case, it will return, it will add B for each column. So if you see, this is our original 5, 6, 7, 8. So this is of our original image, which is 4x2. And for B is just a 4x1 matrix, which is 4x1. In this case, it will add the matrix B to each column, this one and this one. So that's why we can return a new value. So if they're not the same size or they're not even compatible, you can not add two numbers together or two matrices together. So here's a table about the element-wise and matrix arithmetic operators. And for example, we have plus minus and element-wise multiplication and matrix multiplication. And we have some other operators here. And for time reason, I will not go through all of them, but you can definitely try all the operators after the lecture. And second is the relational operators. So in Matlab, we have some like we have the less than or equal, greater than or equal, we have equal, and we have not equal. So those are some common relational operators in Matlab. So let's say some examples here. So we have two matrices here, the matrix A and matrix B. And we see that the operation, when we use A equals B, it produces a logical array of the same dimensions as A and B. So you can see that we have ones in these locations. So if they are equal, 5, 5, 6, 6. So where the corresponding elements of A and B match each other, and zeros elsewhere. And again, with the relational operators, both operands must have the same or compatible size. Okay, the next one is some logical operators. So you see we have element and, or, not, a scalar and a scalar or. And we have some other common functions here, which is the exclusive or. And remember that for exclusive, the XOR function returns 1 at the location only if both element operands are logically different. And if they're the same, it will return 0. And we have two other functions. We have two more functions here, or and any. And although you may not use them frequently, but they are very helpful at in some cases. And all function returns 1 if all the elements in a vector are non-zero. And otherwise, all will just return 0. And for any, it will return 1 if any of the value in a vector is non-zero. Otherwise, it will return 0. So let's see some examples. So here we have some logical functions, and you see we have A and B. So for XOR, if they are different it will return 1. So thus we have 1 here. If they are the so if they are the same, it will return 0. So you may wonder why this is 0, right? So if you look at this, this is 2, this is -1, but we return 0. So the reason is because in logical functions, so any values that are non-zero will be considered as 1. So you see that for the first one, because this is 1, 0, they're different, so that's why it's 1. And for the second one, because they're both non-zero, so that's why they're the same thing in Matlab. So this will return 0. And the same thing for the third one, this is 0. And for the second row, because this is 0, this is 4, they're different. So that's why it will return 1. And this is 1, and this is 0. So that's how XOR works in Matlab. And here we have the all function. So remember what all function does. So if you look at here, if all function returns 1 if all the elements in a vector are non-zero. So you see, because for A, all of them are non-zero values, so that's why it will return 1 for each column. And for B, because the first is 0 and the second one is 0, we have 0 values, and the third one we don't have any. They're all non-zero values, that's why we return 1. And for any, what any does. So if you look at this table, any function returns 1 if any of the elements in a vector is non-zero. So because for in column, and they're both 0, so that's why it's 0. And for the second one, because we have -1, that's non-zero, so that's why it will return 1. And for the third one is 1, 2, so that's why it also returns 1. So all and any are very helpful when you use it for in Matlab when you are trying to find the non-zero values, or you want to find the 0 values. So next is some handle graphics and manipulations. So these are those functions, you may don't use them a lot, but they can help you easily set up some properties in your Matlab. For example, you can use get function, and the first argument will be the handle to object, and second one will be the property name. This will return the value of that property. And the set will be the same thing. You can set the value of that property. And so let's say an example so you have a more it will be more straightforward to show you the example of handle graphics. So for example, here we have a get the GCA function. So what GCA means is get current axis and the font size. So this will return the current font size on the current axis. And for example, I can change the font size. By default, this might be 10 or 12. So for example, I want to change my font size to 24. And you can just type 24 as the third argument. So in this case, it will set your font size to 24. And something else is you can try to get your screen size by using get function 0 screen size. It will return the screen size of the root object. And if you just use get 0, it will return everything about the root object. So a short summary, the root object is the parent object of all figures. Some of its properties belong to the Matlab session. For example, the current figure, and some concern the current computer setup. for example, as the screen size or the pointer location. So try to play with this code after the class, so you can have a more straightforward idea what they mean. So another one is that, for example, you can use get GCA function here. It will return a list of everything you might want to set for the current axis. So that's something about the handle graphics. And format. So in Matlab, you can change the format with the format functions. For example, we use get 0 format. So that will in Matlab that will show you your current data types or format. For example, for my Matlab, is at the beginning is short type. What that means is, for example, when you display pi in Matlab, that will give you something like this, which is a short format. And if you want to display a long list of the pi values, you can change the format to long. In this case, you will get a much longer pi value in Matlab. So here is a table for all the different format types. And for example, we have short, we have long, and for time reason, I will skip this one. So if you're interested in the details, feel free to check this table. So the next one is I want to mention is a function handles. So a function handle is a MATLAB data type that contains information used to reference a function. So you can pass the handle as an argument in a call to another function. And the function handle carries all the information needed for MATLAB to evaluate the function, which can lead to a simpler program implementation. And function handles also can improve the performance in repeated operations, and they can be saved in data structures or files for later use. And the general format for constructing an anonymous function handle is shown here. And you can use the @ symbol in MATLAB. For example, for the sine function, we want to convert it to a function handles. And by typing @sine, this will give us a function handle. And for example, if you want to try the sine pi, and this is almost a 0 value, and so this h pi will just calculate the sine pi for you. So here is another example for the function handles. And you can type an input argument list. For example, here we have at xy, which means we have two variables. And our expression is x squared plus y squared, and we calculate the square root for that. And in this case, when we type R34, this will return the file, right? So here's another example, and we're trying to calculate as the square of x. So in this case, it will be the G3 that will return 9. Oops, I will stop here. So far we have dealt with numerical, logical, and character arrays. And in the following discussions, we will explore another 3 data types that are fundamental, important in MATLAB programming, which are cell arrays, structures, and the tables. So cell arrays. So cell arrays are like lists in Python. So as you know, a matrix is a 2-dimensional array. So in which all rows have the same number of columns, and each column has the same number of rows. So each element of a matrix is a single number. So cell arrays in two-dimensional have the same property in the sense that the two are two-dimensional rectangular arrays. But however, each element of a cell array is a cell that can contain any Matlab arrays. For example, numeric arrays, strings, structures, and which will be discussed shortly, and even other cell arrays. So here we have a list of cell arrays. So we have three different types: a string, an integer, and a range for a range from 2 to 4. And you want to pay attention to the difference between the parentheses and the curly braces here. So if you use parentheses 1, this will return the first array, a cell, which is in the self format. And if you use the curly braces, it will return the content of the first cell. In that case, it will the value of the string. So that's the difference between these two formats. So for example, we have three different arrays. The first one is an image. The second one is something we randomly create. So once we'll just return a matrix with all values equal to 1. And we have a character array, which are two string, a car, dog. And we can put them in cell arrays. And that will give us a 1×3 cell arrays. So you can see there are different data types in this cell array. And the next one is structures. Structures also allows grouping of a collection of dissimilar data into a single variable. But however, unlike cell arrays, in which cells are addressed by numbers, elements of structures are addressed by user-defined name called fields. And fields are appended to a structure using a dot. So for example, we want to use a field within a structure, you just set it and use it. For example, we want to define a person's height, which is 138, and the person's age is 42. And we'll type person in Matlab, it will give you the structure with two fields, the height and age. So here is another example. Here we have a structure, and you can define different fields. So for example, we have the image F, vector B, and character array. So this is, so by putting the dot, you can return the three, you can put them in a structure format. So F and B and the character array are the same with the previous one is here. These are the three files. The last one is the tables. So tables are arrays in tabular form, so whose named columns can have different data types, just like cell arrays and structures. And tables are suitable for data stored in the .csv mode, which means comma separated values or spreadsheet. And although it's common for table variables to have one column, the centroid variable above demonstrates that table variables can also have multiple columns. And table variables can be accessed using dot notation, just like the structure fields and object properties. And Matlab has a large number of data processing and data analysis functions for working with table data, and including import and export from spreadsheet files. or statistical summaries, sorting and filling in missing values, and joining and merging data in multiple tables, and also visualizing the table contents. So here's an example for the tables. And for example, we have 3 variables: area, orientation, and centroid. By putting them in the table function, and it will return a table with the which is a 3x3 table. The first column is the area, the second is orientation, and the third one is centroid. So if you want to calculate, for example, something like the mean of the first column, your area, you can access to the area by t dot area, and then using the mean, it will return the mean value for the area in the first column. And some other things like optimization nodes. And so try to use vectors instead of loops whenever possible. And pre-allocate arrays before you start using them. Otherwise, the computer has to stop and reallocate memory every time you grow the array. And to figure out where you are spending most of your processing time, use the profiler. So what profiler is that if you type profile on, it will turn on the profiler and starts collecting data. And to turn off the profiler, you can use profile off. And to show the result, you can use profile viewer. And again, try to type them in Matlab and see what they look like. So I think I'm running out of time. I will stop here. And remember that for today's lecture, we covered the interactive input-output. We discussed the G input function. And we discussed the RGB and indexed image. We covered the logical and the linear indexing, the operators, the format. And the last one is the cell structure and table. Make sure you know what they mean in Matlab. And I will stop sharing. Let me add my show Discord. So that's it, and that's for today's lecture, and I'll see you next week. Oh, if you have any questions, you can stay online. Yeah, no problem. I'll see you next week. Oh, make sure you finish your quiz and your homework. Yeah, no problem. No worries. I will upload this week's lectures, the slides to my courses by the end of this week, you know. You can take a look at it.
Thank you, Professor.
Yeah, no problem. I have a couple of quick questions about the homework. Can you share the Zoom meeting links? Yes, I will do that. You can. Hey, Vedika, what do you mean share the Zoom meeting links? I mean recordings. Oh, no problem. I will post it. I will post it on my announcement. So no worries. Yeah. Yeah, no problem. See you. Michael is here. I think Michael has some. Matthew is also here.
Hello.
Hey, so what's your question?
I just had a question on like the very first part about setting up the directory. And I just wanted to make sure that like when I was inverting my colors, that I was doing that right.
Yeah, okay, let me stop recording. So